Right, we are going to use recursion to solve a famous puzzle, and that is it's called the Towers of Hanoi. It's based on an ancient legend that there are these monks and that they have these towers with diamond spikes or diamond discs. There are 64, and they're moving them around. And the idea is to move all the discs from one tower to the next tower, the third tower, one to another tower. And once that is done, the universe will end. Let's hope that doesn't happen, but yeah, let's hope. So, there's a link on the webpage where you can play this game interactively, and you can play around with solving this. So, you can fool around. Let's see if I can do it. Okay, 3 is easy. I'm supposed to move the towers to the last disk. And I did, but I took 9 moves, and the minimum is in fact 7. So that perhaps was not very clever. But we can solve this using recursion, and it's really a good illustration of how to think recursively. So I'm going to show you the right way and the wrong way. So let's just think about this a little while. If there's only one disk, I can just move it to the final tower. But let's say there are 2 disks. Let's restart with, can I have 2 disks? I can't even have 2 disks. Okay, right. So let's say there are 3 disks. How am I going to solve this with recursion? Well, firstly, there's only one possible move that I can make at the start. I can move the top disk to one of the other pegs. Or you could say there are 2 moves. I don't know which one to move it to, but let's say we move it to the middle one. Now we have a similar problem. Now we want to move this whole stack, which is now 1 fewer disks, to the 3rd peg and put this peg on top. So that sounds like recursion. Move the smallest peg that I can move, then move a tower that is 1 smaller to the last peg, and finally move the small peg to the top of that new stack. That definitely sounds recursive. One way of thinking about recursion is just assuming you can do it. Assuming you have a magic wand that'll solve the problem for n-1, and then all you have to do is find the solution for n using that magic wand. So if I had a magic wand that I could move the small disk to a free peg, use my magic wand to move the whole rest of the stack, which is now 1 smaller, to the 3rd peg and move the small peg on top. This is not going to work. But let's think about why not. Okay, so let's go into the recursion. I move my small disk to the center peg. Then I call myself recursively to move this stack to the 3rd peg. But think about this. When I started out with a stack of n, I had 2 free pegs that I could move the small disk to. When I move the small disk, I'm now occupying this center peg. So when I try to move the rest of the stack, n-1 stack, to the 3rd peg, I do not have 3 open pegs or 2 open pegs anymore. I only have this 1 peg that's available for moving this stack, because this disk is occupying the center peg. Of course, I forgot to mention the rules. You're never allowed to put a big disk on a small disk. It'll break or what have you. So I could only move a small disk onto a bigger disk. So I can't move this middle disk here. That's not allowed. I could only move it there. So in effect, when I ask myself to move this n-1 stack to the 3rd peg, the conditions are not the same as when I ask myself to move the n stack to the 3rd peg. Right, so we have to find a different recursive idea to solve this problem. And in this case, it's not very difficult. We are still going to use recursion. We're going to use the same idea, but I'm going to first do the recursion and then make my one secret move. So my recursive call will be to move not the n stack, but the n-1 top disks to the other peg. So I'm aiming for the third peg, but I'm going to move the n-1 disks on top of my current stack to the middle peg. So let's see. It'll do that and that and that. Magic wand. Now I've moved n-1 to the middle peg. Now I have to move one disk to the final peg, the destination peg. And then I call my magic wand again. And it can solve this problem easily. Okay. So there's a big difference between the first solution where I do a move, recursively move a stack, then do one other move, or what we think is the correct solution of moving a stack magically, doing one move, and moving the stack again. And you can see that I don't face the same problem that I had before. Before, when I only moved the small disk and then magically moved the n-1, I was now working with one hand tied behind my back because I couldn't use the center peg. But when I'm asked to move the top n-1, I have three pegs available, or two open pegs available, so I can easily move the top n-1 to the center peg. Like so. And now when I have to do my one move, I can easily do that and then do the rest of the moves magically again with recursion. Okay, so we're going to use the second solution. The only tricky thing in this problem is keeping track of which is the open peg, which is the available peg or the destination peg. So let's write that. I'm going to move called Towers of Hanoi with 3 disks that I want to move from peg 1 to peg 3. 3, like that. Okay, and public static void Towers of Hanoi. How many disks do I have to move? And where do I move it from? And where do I move it to? Okay, so from is one of my pegs, 2 is my other peg, my destination peg, and there's a third peg that we don't know what its number is. But I'm going to calculate that number using just from and to. So if we call the pegs 1, 2, and 3, let's just go back here. Peg 1, 2, and 3. So 1 plus 2 plus 3 is 6. So if I'm working with peg 1 and peg 3, 1 plus 3 is 4. If I subtract that from 6, I get 2, the missing peg. Or if I move from peg 2 to peg 3, 3 plus 2 is 5. Subtract that from 6, I get peg 1, which is my available peg. So that's an easy calculation. I can calculate that the free peg is 6 minus from minus 2. Okay, so that's my free peg. And remember what we said, we're going to do 2 recursive calls. One to move the top n-1 disks from the from disk to the free, to the final disk. No, to the free disk, yes? And then I'm going to do my one move of the biggest disk to the destination disk, and then I'm going to do another recursive call. So how do we make a move? This little program is just going to print a list of moves of single disks. So I'm just going to say move disk on peg from to peg 2. And then I'm going to call myself recursively. These n-1 disks have previously been moved to the free peg, so I'm moving them from the free peg to the final peg, the destination peg. So once again, we move the top n-1 disks from to, these are bad names, from to free. Then we move the largest disk, which was at the bottom and is still on peg from, move that to the destination disk peg, and then call myself recursively to move the disks that are still on free now on top of that largest disk. Okay, now there is one issue that you should spot immediately. This recursion has no termination condition. So if I call it now, it will keep on going forever, and n will go to 0 and then -1 and -2. Recursion will never stop. So we must have a termination condition. And for us, that is going to be if there is only one disk, then we just move it. So in fact, what we can write is, if there is more than one disk, do the recursive solution. Move the one disk. And let's delete that, put that in there, then move this down. Okay, so I do the recursive calls only if n is bigger than 1. Because otherwise, if n is just 1, there is only one disk and there's nothing to move recursively. Right here. So let's see if this works. I'm going to run it. Let's open the console, run, and I get a list of moves. And now I'm actually going to play those moves. Let's put this here. Okay, right. Let's move this over and restart. So move the disk on peg 1 to peg 3. Move the disk from peg 1 to peg 2. Third move is move disk 3 to peg 2, 3 to 2, 1 to 3, 1 to 3, 2 to 1, 2 to 1, 2 to 3, 2 to 3, and 1 to 3, 1 to 3. And I've done it in the minimum number of moves. That's great. Let's see if we can do this for level 4. Let's just move that down. Okay, so 4 disks from peg 1 to peg 3. And I'll speed this up to spare you all the details. Those are my instructions, and 4 disks. Okay, here we go. It seems to work perfectly. So this is the Towers of Hanoi recursive solution. It's an illustration of how we think about how to use recursion. Remember that idea of having a magic wand. It's very difficult to get used to, but once you've mastered it, it's a really powerful technique for solving problems in computer science. Well done.